Just one final check. Thank you so much for the thumbs up. That really
Yes.
helps. All right. Hi, so welcome to this 2-day course for hands-on machine learning essentials. I think the course might be announced slightly different in the meeting, but typically I give this course as one large course where we will both cover theory and do a lot of exercises to get you both also really on the hands-on part. So just as a short introduction, my name is Doppenberg. I'm living in the Netherlands, working at a company called ORTEC, which is located in Zoetermeer, which is, for people that know it, it's near The Hague. Before I worked at ORTEC, I studied applied mathematics for 5 years. And after that, I joined ORTEC, now working there for 4 years and as an analytics consultant. And I've been mainly working at optimization projects at Shell. Typically, I'm involved in building very large-scale AI solutions where both data science and optimization comes together to, for example, optimize production. In my free time, I do a lot of board games, play the piano, and also love to do sports in the other times. So hopefully you will enjoy this course. The course will be consisting of the following program. Today we will start with a small introduction to machine learning. I think there has been already some small introduction by other courses, but I think it's good to no matter what, be on the same page. Then we will cover today 3 important and basic algorithms that are algorithms for regression, classification, and clustering. And for each of these algorithms, we will also cover exercises. So typically I will do the regression theory first, then do the exercises. Again, theory, exercise, and theory and exercises. In day 2, we will cover, I think I always find this bit a little bit more interesting because we will also talk about model quality and selection, which is typically a difficult topic. And we will also cover more complex and strong methods in the ensemble methods. Instead of doing several small exercises, you will have more freedom to pick up your own kind of project. And I will give you a data set, but I mean, you can do whatever you want in the project, what you have learned during the course. And so you will have a lot more freedom during those exercises. So let's get started.
David,
Yes.
just before you get started, as your background is in mathematics, I don't know if you could refer me to any class that I can take regarding the linear algebra or mathematics for machine learning. That would be very interesting for me.
Okay.
I studied that in school a long time ago, but I am a little bit rusty, and I want to be able to understand the concept behind it. And I think this is very important skill. So if you could
right.
have
And
suggestions over that.
With linear algebra, you really mean matrix calculation and that, or what?
Yes, exactly.
Yes. All right. I can't refer you directly to something, but I will try after today, see if I can find something interesting. Thanks for the question. Let me find the second slide deck for today. I accidentally pressed refresh on the browser rather than presentation mode, which is accidentally the same button as presentation mode here. So just to check, can you see the slide deck again? Yes, thank you so much. Yes, thank you so much. All right, let's get started with the introduction. So in this introduction, we'll basically cover why do we actually need machine learning methods. We will cover the general concept of machine learning methods, because that basically doesn't really matter which kind of algorithm you pick, the general idea typically stays the same. And finally, we will also discuss what is a good model and when is a good model, which is already, let's say, a peek to what we will discuss tomorrow. but yeah, already interesting to start a little bit thinking about this topic. So first of all, machine learning is used in a lot of different areas. I think currently we are well aware that facial recognition is becoming more and more a part of our daily life. Um, as you can see here, there's a small picture where an algorithm tries to classify faces. I don't think it's particularly good currently, but you can see an algorithm tries, yeah, gets some kind of an image as an input and tries to find the face. It needs to be learned beforehand uh, on some kind of data set, and then you can, for example, assess the quality. But uh, it's not only facial detection. Of course, there are a lot more areas where you can use machine learning. So there are several here. So I think a very well-known one is credit fraud detection, where based on your transactions tries to find anomalous or weird transactions that should not be part of your normal set of transactions. So there are a lot of different areas where you can apply it. One area where I really like where you can apply this, for example, in mastering board games or games in general. There's a very nice documentation about how Google built an AI called AlphaGo that beats the human Go world champion, and it was actually pretty historic because chess, I think we are already able to beat human players in the end of the 90s. But Go has so much more state spaces, and with state spaces, I mean options this board can be in. So you can see each of these crossings can be either white, black, or empty. And then if you, I don't actually know how many of these crossings you have where you can place a yeah, player piece, but you can imagine there's a lot of options that you need to go through in order to actually optimize your strategy. And they were actually thinking that it would still take years for machine learning to catch up and actually beat human players. I think there was already a lot of in the history they tried a lot to beat the human Go players. They were actually not able to do so. So um, at some point, they started testing their AI on the European master. I think that this European master is still not that good, or not even close to the actual human, the Go master world champion. But at that time, the AI was already able to beat the European champion 5-0, and then it went actually up for an actual confrontation with the world champion, and then also succeeded. I think it was actually 4-1. Uh, and it was actually, it's really an interesting documentation, that's not the correct word, video about this on Netflix, because actually this person was really baffled or almost ashamed that he lost from a computer. So there's always also, it's not only technology, there's also still human emotions involved in these kind of projects. So if you're interested, would highly recommend watching that. um, but in general, those machine learning should not just be used for optimizing board games or whatever. In general, machine learning should be used for exploring, yeah, or studying algorithms, or yeah, constructing algorithms that can learn from and make predictions on data. Especially the data bit here is really important. That's also actually why machine learning is booming in the last 10 or 20 years, because we have a lot of data being generated every second. Actually, we have so much that actually in the last 2 years we have made more data than in the entire history of the human race. And I actually think that holds for any year. We are really generating data on an exponential curve. Means we have a lot of data also to learn from and get impact and insights from. So a good example here is if you have, for example, a sensor somewhere in a factory that measures the temperature of some kind of process that you need to monitor, because it's very important that these temperatures are not going out of range. You need to monitor that, for example, every second. You can imagine if you have a sensor generating a data point every second, that already means 60 data points a minute. Then again, an hour, you have 3,600 data points. You're really generating a lot of data on a daily basis in that sense. And I guess when you're going to store it in, for example, an Excel sheet, you will actually run out of space quite soon. It's also why we need additional methods here. But for big data, we're not only interested in let's say the volume of data we have, but there's also you have a lot of different things we measure. The veracity. We also have the um, I'm sorry, I'm a little bit forget about the other V's, but basically, big data consists of 4 V's, meaning that we just have a lot of rows, so a lot of observations. We have a lot of different things we measure, and that's why it's really interesting to learn from that. And the second thing we actually need to process that much of data is to have computers that can actually handle it. And maybe you already have heard about Moore's law, but basically Moore's law is saying the performance of computers actually also exponentially growing. And because of this, every year we can build more complex machine learning models and use more data to train them and train them even faster, um, which makes it very interesting for us to yeah, to start exploring this field of yeah, of science. So in general, as I already said, machine learnings are typically used to predict something in the future. Prediction can actually be separated in 2 different topics. So we have prediction, really the prediction. So what will be the response given some kind of inputs I received? So really seeing if I see the weather of today, can I try to predict the weather of tomorrow? But also there is this bit about inference or causality, which is also very important because we try to actually identify the relationship between what we measure and what we try to predict. And this is typically not something very easy. I will try to explain it a little bit with the following example. So this is really about causation is really not the same as correlation. And this is a really classical example. So suppose you have you want to build a machine learning model that tries to predict ice cream sales. So what you do, you try to find some kind of data source that you can use to predict the ice cream sales. So what you could find if you're, for example, only looking at correlation, is that when you use the number of sunburns as input to your model, you can actually get maybe a good insight in ice cream, because this might be a correlation of 0.8 or something, and you think that's very nice. And now I can build my linear model. But actually, when you think about this, it's a kind of weird that you use the number of sunburns to predict ice cream sales, because actually there's something else that is behind both. Typically, the sun is causing these sunburns, and also when it's hot, you tend to like eating more ice cream. So although these correlation algorithms typically use something like Pearson correlation, are very nice in automatically identifying data sources that work really well for what you want to predict, you always need to be very careful what you use, because correlation is definitely not the same as causation. I think this example clearly shows that. So in this case, you definitely want to build a model, inputted the number of sun hours that day and the temperature, for example. So moving on into more depth in machine learning, there are basically 3 different categories of machine learning, called supervised, unsupervised learning, and reinforcement learning. Um, in this course, we will focus on both the supervised and unsupervised learning, but not so much on the reinforcement learning. So supervised learning, you can think about regression and classification. In these cases, you have inputs and outputs available, and you're going to try to train your model on that. In unsupervised learning, you have your inputs, but you don't know your response variables yet. So you don't know which labels you're going to predict. Reinforcement learning is again very different. This is more like the AlphaGo example, where you have, for example, the official definition says an agent is taking actions in an environment and receiving delayed rewards. So an environment could, for example, be a game like Go, and you can take actions, for example, placing one of those player pieces on the board. Based on your action, you get some delayed rewards from your board game. or from your video game or whatever, and you try to maximize those rewards. It's also very interesting field of machine learning. It's I think a little bit more difficult, and that's also why it's out of scope for today. To show you more clearly what the difference is between supervised and unsupervised learning, I think this graphic is really powerful. So in supervised learning, if you have your data set here containing 8 data points and 2 variables, x1 and x2, you actually already know the labels of this. So you already know, for example, if I try to predict whether someone is doing fraudulent transactions, then for example, you already know the blue ones are not fraudulent, the red ones are fraudulent, and then based on that, I can try to train a model that learns this kind of patterns. In unsupervised learning, you might get the same kind of 8 data points, but you don't know anything more, and then the algorithm needs to find out on its own what the set is of fraudulent and non-fraudulent actions. Typically, clustering can be used for maybe customer segregation if you have different kind of customers, so young and old. You might want to or you don't know what kind of different customer groups you have. You want to use a clustering algorithm that does it automatically for you based on some sales information you could have, for example, on your customers. So for each of these, I want to just show you a couple of algorithms you can use. So the bold ones, although they're not that clear, are the ones that we're going to cover. So if we're talking about supervised learning and doing regression, we will cover linear regression and only linear regression. The regression tree we kind of cover in the second day. Also, the ensemble methods will also be covered the second day. For classification, we have logistic regression, a classification tree available, and so the logistic regression will also be part of today, but the classification tree again tomorrow. Random forest and tree ensembles again will also be part of the course tomorrow. Finally, for clustering, we will just cover k-means. Then a very important topic when you're performing machine learning studies is actually the question, what is a good model and when do you consider a model to be good? This is a very difficult question because there is this balance or trade-off that you have for models. In general, when you want to have a very accurate model, your interpretability of your model goes down. And the other way around, if you want to have a very interpretable model, your accuracy will go down. A good example here is if you want, for example, to predict something like ice cream sales, you could just use linear regression. That's probably the most basic method you can use. It's very interpretable because you can basically see whenever I change my variable a little bit, what happens to the output. But that also means because of the simplicity, it will basically cost you in accuracy. The other way around, you could also just deploy some kind of neural network to do your predictions for you. But then again, it's very hard to see how did you actually make that prediction. Nowadays, this is a very important topic because more and more companies are using machine learning algorithms to do the work for them. But if you're, for example, an insurance company and you're handing out loans, but you have a model that you can't explain, you're actually violating certain laws because typically each customer should be able to get an explanation why he got rejected. So that's why this is more and more important nowadays. And we need to be very careful deploying difficult but maybe accurate models in these cases. So if we are going to do a machine learning project, we're interested in basically the structure. So what do you need? So at first you need your data set. So your data sets consist of observations and features, and typically something you want to predict. So there are different namings if you would go on the internet and research yourself for these observations. So in the case of an ice cream sale, you could think of observations as a day, where you made as a day, and then as features here. So the axis here could be the number of sun hours, the temperature, number of the rain, and that kind of stuff. Typically, I will refer to the features here, or the axis, as features. But other people or other specialties will call this is slightly different. So if you would look for really statistical reading materials, you will probably find something as independent variables, and it's basically just the same thing. Also, attribute is something you will typically see. For example, when we will do some logistic regression exercises, you will see that the Python library that we're going to use is, I think, either using independent variables or explanatory variables, while the other one will use features. Then the column here, and this is only in the case of supervised learning, you will have a column with a target variable. I will always call this a target variable called y. Basically, this will be the thing you're trying to predict. So this would be, in our example, the number of ice cream sales. But these are also referred to, again, to different things. So if you're more in a statistical background, this will typically be called a dependent variable. When you're talking about classification or classification, you typically talk about labels. But again, these things are basically just the same thing, so be aware of that. And when we're talking about big data, it's basically just that you have a lot of columns here and a lot of rows. Yeah, basically so many rows and columns that it won't fit in your Excel. So when we have our data set of historical data, we want to train our model based on that. And the model is typically, you could think about an algorithm or a classifier. Then when we have trained our model and we get a new observation where we don't know the target variable yet, we feed this new observation into our model based on the features that we have. It will generate a new prediction. That's basically how prediction works for machine learning. Again, to show you two different examples of regression and classification. So in this case, we have basically twice the same data set. So this data set consists of persons, so names, and each person has an age, a gender, a country, and a height. And suppose you would get this data set and you want to do a regression study on it, you would look for something that's continuous, meaning it's actually a number. So if you want to do regression, you would, for example, look at the height or the age. In this case, we want, for example, to look at the height, predict the height based on the country, gender, and age. On the contrary, if we want to have this, if you have the same data set but you are interested to do classification, you typically look at something that's discrete, meaning it could be more like, so not typically numbers, but more like categories that you want to predict. So in this case, a country or the gender would be a discrete variable because it can just take a limited amount of options. So in this case, for classification, we will try to classify the gender based on age, height, and country. Although this example is typically not something you want to do in practice because it contains a lot of personal information. I saw there was some kind of question, I think, Marta.
Yeah, so well, there's a question about the graph about Moore's law that looked like the curve is flattening. And the question was if it's true or and how will it impact machine learning development?
Very interesting question. Maybe first cover that one. So sorry for just covering these questions so late. I think the idea of why Moore's law is flattening is because I'm not a computer expert, but I think they try to make these chips and they can put more transistors in a certain space. So every time they are able to fit more transistors in a smaller space, you can see an increase in computer power. But at some point, you're basically, I'm not sure whether that's molecular level or atomic level, you're basically reaching that size or scope of trying to make more transistors, adding more transistors to your chips. That is because becoming very hard to actually make, to do that. So I think yes, I think this is true. Exactly, someone saying a quantum computer might defy this law. Yes, but that's also not really a transition. A classical computer anymore. So it will come at a lot of different um, difficult. We'll have other difficulties. I think typically quantum computers are not yet at the point that we can start using them in practice. But indeed, we at some point maybe we won't use classical computers as we know them anymore, but move towards different computers that don't necessarily follow this Moore's law. But basically, what also, so suppose you cannot make any of these changes on this very small scale. What you can basically do is just add more and more computers. So basically, if you're talking about ChatGPT, you really, I don't know how many computers they actually have in that location to actually train the model. But basically, if you just need more computing power, you just purchase more and more until you have enough. So that's also an option. But yeah, there will at some point definitely be limitations with the current setup. I don't know when we will reach them, but yeah, I think it's a very interesting thing, at least to think about. Hope that answers the question more or less.
Actually, it was
Okay.
an observation prediction. Was
Okay.
not any best.
Okay. Yeah.
So it might not be possible to continue double
Yes.
the processor power
Exactly.
every 2 years, but at
Yeah.
some point it became I would say what's called fulfilling prophecy.
That's true.
Until a specific time where it's not possible basically to keep doing it.
Yeah. Did we have more questions?
Yeah, there was another question by Valerie. Do you feed the data directly into the model, or do you need to paste, I would say, or paste before, or I don't know.
Pasting, as I mean copy pasting, is
No,
that
parsing, sorry.
parsing?
Parsing. Okay. Sorry.
So can you maybe explain it a little bit more, your question? What do you mean with parsing?
Well, so my understanding was that very often you actually have to prepare the data from the table to feed it into the model, and I thought that was generally called parsing.
Yes.
Just make sure that you're comparing apples with apples.
Yes, and that typically really depends on what kind of algorithm you use. I think if you're using neural networks, then you're really right, because typically neural networks work best, I think, if each feature is normally distributed between standard normally distributed. So you need to do some kind of transformations in order to get that kind of data. But when you're, for example, doing decision trees, I don't think you need to do any kind of that stuff, except that you still need to do a lot of pre-processing of data, because these models, they cannot deal with missing data, for example, and when you're talking about parsing, for example, when numbers are in a string format. So yes, it's not just there are typically some steps required in order to actually feed it into the model, but that's what will not be the scope of today. In our current scope, we assume some kind of data engineer has prepared our data set for us completely, and then we can directly feed it into the model.
Okay, I think that answers the question. Then we have another question by Ayman. I'm not sure exactly what he refers to, but is it required a laptop or a PC with great specification to work for these models, machine learning models, or the field of machine learning?
Yeah. When you would have asked this question a couple of years ago, I might have said yes. But in the current state, you typically don't train these models anymore on your own machine. So you will train them, for example, on the cloud. And then the only thing you actually need is just some kind of an internet connection and a cloud service to perform this. So currently not. Typically in my work, I think the machine learning models that I do are on a smaller scale. So those might be like I have just 100 or a couple of hundred observations. Then you can definitely do them on your local machine, and then it might take 15 minutes or so if you have a very complicated model to train it. But in general, I would say you can do most of this on a not so powerful machine, but if you really want to do something like neural networks on a large scale, then probably you want to do some kind of cloud service. But then again, you don't need a very good hardware. You just need to make sure you get your cloud service correctly chosen.
Okay. Another question is, when the value that I am trying to predict is true or false, what model should I use?
Yeah, so that's a good question. I'm not sure whether I still have those slides in here, but when you do something like true or false, that's, let's say, a limited set of categories, meaning that it's not an actual number. And in that case, you need to do classification. Good question.
Okay, and then user segmentation based on user activity on a particular software is called regression or classification, as users' activities changing over time, and it is also called classification of users.
That's a difficult question.
Yeah,
Um,
maybe if you read it.
I think I can probably read it myself. So user segmentation based on user activity on a particular software is called regression or classification, as user activity is changing over time. So I think what you are trying to refer to, and please correct me if I'm wrong, it feels like you're doing something like an anomaly detection, basically saying a user is performing some actions with software, and this software is, for example, logging the activities, and based on the activities, it tries to predict whether this is changing over time. I think something like that. Hopefully.
Yeah. So
Yes.
can I for a bit? So my question is, let's say in a case scenario, I want to make persona segmentation for marketing messages or sending personalized messages. In that kind of scenarios, I will need to track the user activity based on their behavior on the platform. Yeah. So in a way of in that kind of case scenarios, what should we call it? Is it called regression or is it called classification?
Okay, I think in this case, if I understand it correctly, it's neither, because I think what you're trying to do is clustering. I feel like, because based on activities, you're trying to find different groups of users, right?
Yes, yeah, it is true.
Yeah, I think this is clustering, but we will see some, I think, better examples, and then we can recheck whether this is actually true, but we will cover that later today. Thanks for your question.
Thank you.
Yeah.
Okay, we have one last question for now. Is there a minimum amount of data that is required to train at least the simplest model?
That's a very difficult question, because it depends a little bit on what you consider to be minimum. If you're talking about linear regression, there's a very easy minimum in the sense that you only are able to draw a line if you have 2 data points, because that's basically the minimum requirement to draw a line. But I think that's actually not what you are after, because typically just 2 data points will not give you a good linear regression model, because it will not be robust and will probably not perform well. So that's why it's actually a very difficult question you have. Typically, I would say the simpler the model, I tend to say you need less data. So in order for a neural network to perform well, I think you need a decent amount of data. Same holds for example, for ChatGPT. that will not work with just 1 million observations. It really basically needs the whole internet to start performing very well. But still, I don't think that's really a very good answer to your question. And I think the best answer I am able to give you is that it is context dependent. So it depends also on how difficult your problem is and how good your data. So if you have like very, very good data, then probably you need less data to train your model. But if your data is very noisy, then you probably need way more data to get the correct relationships. So I know that's not really a satisfactory answer, but I think that's just the way it is. It's not as easy to answer this question, unfortunately.
Okay. Thank you very much. I think we can keep going for now.
Yeah. Thank you.
Thanks.
I will try to have a little bit more moments during the presentation to answer these questions intermediate. Again, thank you so much for answering asking me questions, because that makes this a lot more interactive and interesting.
No worries.
I think we left off a little bit here. Yeah. So now I was basically saying that you can have one data set, but you can have multiple machine learning projects. So just to recap, if you want to do regression on this data set, you typically look for numbers. So in this case, you want to predict height. But for classification, you look at something like a discrete set of labels. And in this case, it would be gender, but could also be country. Then for clustering, you could also have the same data set. And what you see here is we don't have that orange column because we basically don't have labels or don't have that target variable yet. So in this case, we just give this data set to the clustering algorithm. Maybe you need to say how many clusters you want to have. And then it will try to find the clusters for you. And in this case, we basically said to the algorithm, find 2 clusters. And then in this case, it found 2 clusters, one containing George, Joyce, Jesse, and Jivan, and one containing John and Jack. If you would look, for example, at how these clusters were created, I think typically the most easy one to explain would be, for example, age, because you can see the average age here is around 5, while the average here is around something like 40. So this is a way to look at these clustering problems where you don't have this response variable. I think I already saw a question coming in. So about handling missing data.
Yeah.
So that is unfortunately not really part of this course, because we're really just focusing on the machine learning algorithms themselves. And where to find and obtain those relevant data sets. Typically, you could, for example, look at a website called Kaggle, I think, which is a very nice resource for free data sets that work pretty well generally. And nice thing is also there that a lot of users made notebooks, so Python notebooks, for you that you can see, such that you can also learn from what other people do. So Kaggle, as in Kaggla. So one other source just for exercise is typically, if you use a Python package, is that these Python packages come with default data sets that you can use. These default data sets typically have very nice behaving data. All right.
Yeah, I can save these kinds of questions, and then maybe you can answer in an email, and we can share with the
that's a
or
very
on
good
Slack.
suggestion. Yeah, I like that.
Okay.
Moving on to the art of machine learning, and I always find this part really intriguing. The art of machine learning is really about making sure you're not underfitting your model or overfitting, and I will explain what that basically means. Underfitting and overfitting. I will typically talk about this like that, but if you read other sources, they also call this the bias and variance trade-off. So a normal machine learning project basically starts with splitting your data, for example, in a test and training set, and then your model is only trained on the training data set. And then you can test the performance on data that has not been seen yet, to get some insight on the actual performance of your model. And that's actually what you see in this picture. So there's this training error, meaning the error the algorithm is making or the machine learning model is making on the training set. So this gives some insight in how well it's behaving on the training set. The more complex your model is, the better it will work. The less errors it will make. So if you think about a linear regression model, the most simple one will basically a linear regression model where you only have one feature. So one column to predict your target variable, but you can make it more complex by adding more and more inputs to your model. And so you could, for example, just give it 1 million inputs, and then it will probably be perform a lot better, meaning that the training error will go down. Simultaneously, you will also have this set aside test data set, and that can be used to see if, because the model is actually not trained on that data, you can see how well it's actually performing on that data set. What you see there is that when you start making models more complex and more complex, the training error is going down, but the validation error is typically going up, meaning that your model is probably learning random noise, for example. So just really weird it will all pick up basically every pattern. Although that will reduce the training error, in practice you don't want that, because that random noise that your model picked up is something you don't actually want to pick up. But more complex models will pick that up, and that tends to lead to higher errors in your testing set. The other way around, if you have a too simple model, then you just make it too simple, meaning that you might miss important things in your relationship. So for example, if you that's a difficult one, if we're again talking about ice cream sales, if you would just include if it's going to rain today as a feature, that might not be that good, so you will have a lot of error. And then because you really need to have, for example, to have the temperature. So this balance between making your model not too simple but also not making your model too complex is typically something that takes a lot of practice. It's really not easy, and I think I really like these visual examples because it really shows you what is going on when you make things too simple or too complex. So if we're talking about overfitting in regression, the most simple model you would have here is basically a straight line. And although in this picture it looks pretty okay, you might miss a lot of important things here. The other way around, if you just make a very complex model, you can see this line is basically going through every data point. And basically on the visual, you can already see this is a model that you don't want, because this doesn't really look like a realistic relationship between the features you have. And in this case, the ideal fit would be something like 3, which catches this kind of, this could be like a seasonal component, because with ice cream sales, again, typically in the summer, you have more sales, and in the winter, your sales will be at the bottom. And this seasonal component could only be captured when you make your model. You have just the right amount of degree here, or complexity in your model.
We have two questions. How do you reduce retraining time and improve the robustness given different heterogeneous data?
The robustness, I think I hope this will be something I will cover later on in this course. I will just pause that question for now.
Okay. And is there a range of degree for ideal fit?
No, so typically not. So that's the whole issue. So in this case, it's very obvious, because now, for example, again, with the ice cream stills, you already know there should be some kind of seasonal component. So at least you need to make sure your model can capture that. But that doesn't mean there will not be linear relationships. That's just a straight line. So that really depends on your context. But I will tomorrow I will show you how you can basically make sure you're not in either one of those cases. So this is just really as an introduction to what overfitting basically or underfitting means. In the second day, I will give you some tools to actually evaluate whether you're overfitting or underfitting, because luckily there are some tools that can help you with this. But for now, I will also pause the details because I think that's better to do tomorrow.
Okay, thank you.
All right. So this was, let's say, a nice visual example for regression. I also want to give you an example for classification. So for classification, in this case, you have like you want to classify whether it's a circle or whether it's a cross. So again, the most easy model would be like, let's say, some kind of a linear line, which is the border between what is a cross and what is a circle. So everything on this side of the cross of the border will be a cross. Everything on that side will be a circle. So with this very simple model, you actually see you already make a lot of errors on both sides. So you might, again, want to make your model more complex, but if you make it too complex, you already get these really weird shapes for your border. Basically, if you're making it too complex, it will start really drawing these borders around your data points, such that it will have a 100% accuracy. But again, this is something what you don't want, because these X's here could also be, let's say, errors in your data set. So you don't want to fit or overfit, in this case, on your errors in your data set. And in this case, again, you want to be somewhere in the middle. So you will end up with this nice parabolic curve or border, where these x's, because they really look like they should actually be circles, are actually considered circles by the model. I don't have any example yet for clustering, but we'll also cover how overfitting works for clustering. So one easy way, now easy, that's not really the case, but to make sure your model is robust to overfitting, what you can do is just have a lot of data. So the more data you have, the less likely your model is to be overfitting. And you can actually see this in this example. So again, we're talking about a regression use case where we try to fit some kind of a prediction model through the data points we have. And we see the green line here is the most simple model we have fitted, and the red line is the most complex model we fit. And the way I can see that the red line is the most complex model is because it's showing these kind of weird curves. That's only possible for complex models. And in the left picture, we only have 15 data points. So you can see in this case, the red line is definitely overfitting. The green line is probably okay because it has this nice seasonal trend. Suppose you would fit exactly the same models, but then you just increase the number of data points to 100. You actually see that both models will show you the same, are almost the same. So you see, if you have more data points, it doesn't really matter how complex your model is, because if you make it too complex, because probably it will be okay because you have enough data points. Again, I don't know any kind of good relationship between complexity and number of data points. But this is just to give you some insight in how you can make sure you don't end up in overfitting. So one option here is just having more data. Problem is, I say just having more data. That's typically not as easy in practice. One of my data science projects, I had a data set that contained so models fitted for a certain valve in a pipeline, and these models were trying to predict whether these valves in this pipeline would break. It's very important to predict that, because those could cause could pose risk to the health of the employees there. So I basically had a data set of random models that were fitted on the data. And then for each of these models, they captured some kind of performance indicator. So it was just, for example, saying how many errors the model made and that kind of stuff. But the issue with this data set is that they classified each model as good, okay, or so average or bad. And that process was that labeling of the models was done manually, meaning that one data point in my dataset took an engineer at the factory about 2 hours in order to get a decent label on the observation. Meaning that because I had 100 data points, that basically took them 200 hours to create my whole data set. Of course, I wanted to have 1,000 data points to make sure my model was performing better, but that would require them to spend an additional 800 man hours to generate my data set. That's typically not something they have the time for or the money, because that's basically just a very costly task. And then in these situations, you even don't know if more data means you can actually get the benefit, because at that point in time, I just started exploring whether we could actually do the classification problem there. So maybe it would have been 800 hours they spent without any impact. So although I can easily say just have more data, unfortunately that's typically not as easy to come by. I think a lot of questions came in.
Yeah.
Or not?
So we have one that asks how fitting is measured and if there are thresholds for a good fit.
Yep. Again, this is the introduction. When we talk about each algorithm, I will explain to you the quality of fit. So
yeah,
we'll come to that. Yeah.
Hannah shared a link saying that the elbow method could be interesting here.
Yes, we will cover that during the course.
Yeah. And then we have a question: is overfitting always a bad thing for a model? And is it comparable to specificity and sensitivity used in statistics?
I think you must have some kind of background already, because specificity and sensitivity are already really machine learning terms. But to your question, is overfitting always a bad thing? That's a very difficult question. I would say no. So it's not always a bad thing, because if you don't have a lot of data, you're basically forced to overfit. So if you just have, in this case, for example, 15, so not this example might be bad, but when you're doing decision trees, and maybe we can cover this question again tomorrow when we cover the decision trees. In certain cases, if you just have 20 data points, you could make a very simple model, and that simple model would basically just be able to make one decision for you, and you end up with a model that's just too simple. So maybe I can just explain it here. In the most ideal case, you have this nice curve and you have enough space in this complexity bit. But in certain moments, if you, for example, if you don't have a lot of data, there is not really this nice trajectory from going from underfitting to overfitting. So in certain cases, you might go, if you just increase your model with one additional complexity, you might go to overfitting directly. So I would typically say, in general, I would try to avoid overfitting. Overfitting basically means you're trying to overfit on errors on your data. So really, I think this is a good example here. I think clearly here you can see overfitting is bad, because you're trying to find the relationships that are not there. That's basically what overfitting means. But in certain cases, you just don't have enough data, and then the only option you have is try to get a good model, and then that might result in overfitting. Do anything about it. So interesting question, but it's not as straightforward. Yeah.
I mean, I'm the one who asked the question. So the reason I asked this question is actually coming from, I did some medical research, and usually in medical research, we balance between, if we have like some medical tests, we balance between, the sensitivity and specificity of the test, depending on the outcome, what we are measuring. Let's say we are measuring some very, very serious disease, we might be more inclusive, and we accept, we want to be as inclusive as possible. So we want very sensitive, even though sometimes we might get some, what they call it, the false false positive. So like even if I take more cases that are classified as positive when they are not, just because the disease is very serious. So here I need the specificity to be high, and I just think about it as compare it to like overfitting it. I need to ensure that my model is actually capturing everything, versus another case where it is where, let's say, the cost of treatment is high, or sometimes the treatment itself might have side effects, unfavorable side effects, where I need also like high specificity also. I'm just trying to link those things together.
I think that's an interesting question, and I'm not really sure whether this is directly related to underfitting and overfitting, because when we're talking about choosing a specificity versus a sensitivity, you're typically this is so sorry for people that have not covered this bit yet, but I will, just for the sake of the question, dive a little bit into too much detail already. But just for the question, you have this decision boundary that gives you gives you insight in when you actually predict something as true or false, and then based on your choice of your decision boundary, you change your specificity and sensitivity, but it's actually not related to the model training yet. But we'll also come to that tomorrow, so maybe we can again tomorrow dive a little bit more in detail in your question. But I think in general this is not directly related. There's of course some kind of relationship, but it's not directly related. Hope that answers it for now.
Okay, then there was a question about what's n. Somebody already answered that n is probably the sample size, or the number of data points.
Yes.
Yeah. And then what also is the level of complexity?
Yeah, I think level of complexity, I agree, that's for now a very vague term. I'm just thinking how I can explain. Yeah, so if you're talking about a linear model, and we will cover that also today, so if it's not clear now, it will become clear in an hour. The complexity of a linear model is basically saying how many inputs do I have. So complexity 1 would mean I have just one input variable to make a prediction. Complexity 2 would be I have two inputs to predict my target, and so on and so on. So that is how you can look at complexity. In other models, complexity is slightly different, but we will cover complexity, let's say, for each algorithm separately.
Okay. Then we have another question. Is error a good thing in our model? I think this is more of like a set of questions, so I'm not sure if they're all related.
So error is, in general, when you're talking about, that's a very interesting question. I love this question. So typically you would say error is of course not something you want. But actually when you're talking about underfitting and overfitting, if your training model is making 0 error, then there should be some kind of an alarm bell going off saying you're probably overfitting. So in this case, if you don't make any error, be careful, because that could be one of those cases where you're overfitting. But again, of course, you want to minimize the error while not overfitting. So it's a layered answer, I would say. In general, a little bit of error is okay, but you want, of course, to have the smallest error possible. So it's almost a philosophical question.
Yeah. Then what techniques or strategies can be employed to address overfitting or underfitting in a machine learning project?
We will cover that tomorrow
Okay.
at the start. Yep.
Let's see this question. If we make labeling or it is similar to classification, is it very relevant to model classification? I'm not sure about this question.
No.
I don't know if you can look at it.
Yeah, I see the question, but I also don't know.
Can I,
So-
this is,
Yeah, of course.
Yeah.
okay, thank you. It's me who asked this question. What I'm saying is, when we say labeling it's just when we, even you mentioned it in the previous example, it's something we label either with 0 or 1, or either true or false. So, so do you think, I mean, how relevant it is, for example, when we are in our model and we are relying, we either go for the classification or we go for the relation one. So when we say the labeling, is it like some division of a classification, or it's like something we can rely when we are making our model?
I still don't completely understand the question, but I'm trying to answer it. So, sorry, when we're talking about labels, labels are typically, like you say, something like true or false or ABC or yeah, something like that. If we're talking about these kind of labels, that always refers to a classification problem. And that means that your model is going to predict also the label. So your model will also try to predict true or false. Is that answering your question or not?
Okay, so yeah, what I'm saying is the data is very sufficient to just, if for example, if like we're saying only true or false, we have only two options. So is it going to be very sufficient when we are building our model? That's what I'm saying.
Yes, yeah, that is perfectly fine. I mean, that just depends on, again, on your context. So if you have, for example, if you need to predict, for example, if you have a spam classifier of emails, then the spam classifier only needs to be trained on true or false, because it's basically the only purpose it has is saying, yes, this is spam, or no, this is spam. So in that case, two labels are fine. In another case, if you need to predict whether the road's what's it called, stoplight is red, green, or yellow, yes, that was correct, red, green, or yellow, then you need three labels. So again, the context, the number of different labels depends on the context. Hope that is clear.
Thank you.
So can I have one suggestion, please? It's this topic is really important for me personally. So if we can structure the session in a way that we take all the theories first, and then we can ask the questions, so we don't miss anything from the limited time that we have, because I know that we have as well technical time to implement this technically. And I'm afraid to reach to the end of the time and we don't cover all the topics.
Yeah, I think that's a very good concern. I also need to balance indeed my time properly between not overfitting on the questions. So thank you so much for that addition. I think you're right. Indeed, I see we're already covering almost an hour on the introduction. Let's pause the questions for now. And indeed, I will try to be more selective, because then we at least can cover all theory. So thank you for this, Anas. I hope I pronounced your name correctly, but thank you for that. Yeah.
Okay, maybe then we can leave the questions for at the end of each block. Let's say when you want.
That's probably
I can read the
better. I
questions
will
for
do
you.
one overview of all questions and then see how much time I have for each topic related to the questions. Yeah.
Okay.
Very good.
Thank you.
All right. Yeah, let's just skip over this. I'm just thinking. Yeah, this is a nice example. And now I'm going to skip over this example. It's not that interesting for now. So we're talking about underfitting and overfitting. I think Einstein said something very interesting. Everything should be made as simple as possible, but not simpler. And I think that's very true also for machine learning. And just to give you some nice, ideas about why making things too simple is not always a good idea. Because again, if you're talking about, oh, I want to prevent overfitting, then what could I do? Just make things simpler. But the important step is here not making things too simple. So here you see, for example, a picture of two shadows, and it looks like these two people are about to kiss. And you could say this is like dimensionality reduction, because our world is like 3 dimensions, but our shadows are casted in 2 dimensions. So if I would go back to the original 3 dimensions, so making actually my model, would say, a little bit more complex, you actually see that these people are not about to kiss, but they are just about to cross each other on the street. This is basically, it's a very, it's just a very nice visual example, but I think the same holds for training your machine learning models. If you to make it just too simple, then you will, lose the touch with reality. So yeah, it's really difficult to make sure you're not overfitting and not underfitting at the same time. At least one way we can deal with this in general, and not only just overfitting, but one very powerful tool we have available in right now is just making things visual. So if you would just have these 8 data points and you fit a linear line through it, this line will have a negative slope, so it will go down. But for example, you have some kind of feature in your data set saying this is of type blue or type red. And then if you make this plot, you actually see that the relationships for the blue and the red are different. So in this case, just fitting one model would be wrong, because maybe you want to have 2 different models for these 2 subgroups. So I think one very important tool we have available for machine learning is just making a lot of plots of your data whenever possible. So of course, if you have a lot of dimensions in your data, it's not easy to check everything, because this plot, typically a scatter plot only has 3 dimensions, because you have the x, the y-axis, and the color. So that's basically everything you can do on the scatter plot, but it can give you a lot of insight in what you're actually doing. So recommendation here is always make sure to get familiar with your data, understand it, explore it, and make sure you don't miss any hidden relationships you have not seen before. So I think also, for the sake of time, I won't do any breaks. Typically I do a break, but I agree, we spend a lot of time on this, and I think the hands-on bit is very important. So I will just continue. I hope you all are still with a lot of energy and still have enough energy to look at this. If you need a little bit of a break, then I would recommend spend some time on the exercises and manage your own time and take your break, the break you need. But for now, let's just move on to the first bit of actual theory. Button on the web page. I will not use F5 anymore today. I will just use the button here. So we will now cover the first algorithm. This is really, let's say, the easiest algorithm we have, which is linear regression. You could think, why are we actually covering this? Maybe you already have a lot of, you know about it, linear regression. But why I always start with linear regression is that it actually, if you know how to set up a machine learning project for linear regression, that's the same project you could probably just use for more difficult models, but just swap the bit where you train your linear regression with training some other kind of model that's more complex. So that's why it's very important to just also have practice with how would I do a machine learning project with linear regression, because it basically gives you the basic skills to perform machine learning projects for more complex models. And also, and still, this linear regression is still used a lot. In my project currently, I have this optimizer that uses machine learning models to make predictions. Those predictions are still being made with linear regression models. So in certain cases, linear regression models are still a very good tool to use, because it gives you exactly what you're doing. So you can actually validate your model 100%. And in certain cases, that is really required. So although it's simple and you think this is too simple, don't forget about it when you're doing machine learning. So what is linear regression? Again, linear regression is always almost saying it. For us, the linear regression is used for regression exercises. These are typically of the form target variable equals some kind of a constant times a coefficient times x. Although this is a mathematical notation, this x is like a matrix. This basically means this could also be a b1 times x1 and b2 times x2 and so on. So basically saying I have one constant value and then I have coefficients times my features. And again, features are these things on the columns of our data set. So this is a good example of one of those fitted regression models. So you see we have a lot of blue data points here. You can see that those have a trend downward, and when you fit your model, it will fit this straight line through your data points, which is also with a negative slope. Negative slope is basically saying the direction of the graph, so if it's up or down. The nice thing here is that this slope is directly one of the coefficients of our model. So basically, I'm not so sure what it is, but I would say this slope is -3. This is actually, the slope is actually this coefficient. So this coefficient here, if we're talking about this two-dimensional case, can be interpreted directly as the slope of this line. And the idea with linear regression, because of course there are basically infinite kind of straight lines you could fit through this data, but basically the idea is to fit the best line, the best straight line through this data set. Again, we will cover what the best straight line means. So this example we are predicting this thing, I don't actually know what it is, based on this feature. So this is a nice two-dimensional case, but it also works for more dimensions. So if you have not just one x1, but you have more columns in your data set, you can just use more of these features. So that introduces a second coefficient that you need to find with fitting times your second feature. But again, that also works for your third, fourth, or whatever kind of feature you have. And this is directly related to the complexity we have been talking about. If you would just look at the model here with one feature, that's probably the simplest model that you can make. Then if you have two features, that's a more complex model. So if you have a more complex model, you need again to be aware of overfitting. So how do we actually measure the fit or the quality of our model? So if we have fitted this straight line through our data, we can start checking the error of our model, or the so-called residual. That's basically the same thing. Error and residual, you can use them both for the same thing. Error is measured from, so basically you can see what is a good example here. At 6.5, we are predicting this data point on the red line because that's our model. So if we would have, for example, a new observation, but we don't know the target variable yet, with feature x1 equals 6.5, then we look up our prediction, which is around, I think something like 14 or 13.5. And then we know actually this data point here, and in this case it's actually a known data point, we know it should have been around 17. And then we can define the residual or the error, which is basically 17 minus 13, which would be 4. And we can do this for all the data points we have. So basically what we do, we have all these data points we trained our model on, we feed them to our new model, we get the prediction, and we check what is the error of our prediction for that data point. So mathematically, this would look like this. So y here is the actual value of the data point, while y with this head on top is the prediction. And when I subtract those, I get my error. And then I need to do it for all my data points. And then we are actually talking about the residual sum of squares, the RSS. It's a very important measure for linear regression. And this is actually taking all the errors, then squaring them. So this sum basically means I sum the errors over all my data points, and I am interested in my squared error to get a nice problem here. Another thing that's very important, and this is just, let's say, a feature of your data set, is the total sum of squares, which is basically very much related to the variance of your data set. So what we look here is, we don't look at the actual prediction of our model, but we look at the average of our data, and then we look at the difference between the average and each observation. Again, we square it and sum it. And these two things form the basis to actually measure the quality of fit. Quality of fit for a linear regression model is measured with the metric called R squared, which is basically the total sum of squares minus the residual sum of squares, again divided by the total sum of squares. And you can simplify this to 1 minus the residual sum of squares divided by the total sum of squares. And this is also, you can also interpret this as the explained variance of your data, because you're looking at how good does my model explain the variance that is inherently in this data set. Yeah, so before I go to the next slide, so when is a linear regression model good? That is basically when I make 0 error. So again, of course, I said at some point a little bit of error is okay, but mathematically speaking, my model is perfect if I don't make a mistake. So meaning this residual sum of squares should be 0, because then my prediction is exactly the value of the observation, meaning that you just sum 0 squared, which is 0. Yeah. And that boils down to an R squared equal to 1. So R squared 1 is very good. The worst you can go in training, I have to say this, that only holds when you're calculating this for your training data set, is an R squared of 0. And that happens when your residual sum of squares is the same as the total sum of squares. I won't dive into detail why that is, but basically you could think of the worst line you could draw through this data set is just the average of your data, and then everything after that will just improve on that. So basically, when your prediction is the average, these two are the same, and you end up with an R squared of 0. So just to summarize, and that's probably the only thing you really need to remember, an R squared of 1 means you're doing really well, given that you still need to check overfitting. An R squared of 0 means basically the model is not doing anything, so you need to refine. So yeah, I already said this metric doesn't really cover overfitting. So there is a slightly adjusted version of this R squared called the adjusted R squared, which also takes into account how complex your model is. So I won't dive into detail how you can derive this formula or whatever, but basically you can see here this P that we have denotes the complexity of our model, so the number of variables. So again, if I just have one input variable, P is 1. If I would have 10, then P is 10. And be aware that you can never have more. That's not really completely true. So what happens here is that when I start increasing my how do you say it, my complexity of my model by adding more variables, I basically penalize the performance by saying, okay, if I add more variables, then I also should expect a way better performance of my model. So if the increase in my model performance is not good enough, then I should penalize my model. And that's what you see here. So if you, in this graph, if you would look at the normal R squared for different model complexities, you can see it starts to increase and increase and increase. And basically what will happen, I think if you keep on increasing to infinity, at some point this will go to 1. And then at that point you would say, okay, that is a very good model. But you don't want that because of overfitting, of course. So this model, at some point, it says, yeah, the trade-off for adding more variables isn't worth it because you're making it too complex. So the added model performance is not worth it. And you see this adjusted R squared is decreasing. So this is always a nice tool to use when doing linear regression. You can have R² and adjusted R² to see what kind of number of variables would be a good fit here. So with this one, again, it's up to you, but also typically up to the client. Because maybe you want to add, in this case, 10 features or 11, because then you're around here, because then adjusted R² is still increasing. But maybe your client will say, I don't like this, what you're doing, because those features should not be included. I can't really explain with my business knowledge why I should use these inputs. And maybe he's saying, I just want to have those 5. So this is not typically something you as a data scientist or if you're doing machine learning, do all the modeling on your own. It's always good to check with the people that are going to use your model and checking, does it make sense? Because these people know a lot of probably not a lot about the the processes, and they can see if it is making sense what you're doing. I'm going to think about an example here. So if you have a very complex chemical model plant, for example, and you have this distillation columns, and you want to make a model out of that, there's like 1,000 sensors that you could use to model the relationship between the inputs and the pressure in that distillation column. That's very important, because if your pressure is too high or too low, that's very dangerous for the people that are working in the plant. So you want, for example, to have a model that predicts the pressure in the column. Then as a data scientist, you can just use whatever data you want and then think, okay, this is a very good model because it has good predictive performance. But at some point, the person that is actually working in the factory and knows everything about those columns and those sensors that they have, they say, okay, these sensors actually don't make sense because they're just measuring noise, for example, or this sensor is actually measuring not the thing that we should include in the model, or they know a lot about the physics behind these columns. So there's always something you need to check when you're doing these kind of, now in this case, regression models that I used also in that actual business case. Yeah, so this looks very complicated, but we also won't really cover this. So of course, what is important here, we have now covered that we have this straight line, and the straight line is defined by the slopes that we have fitted. The question is, of course, how do we actually find these slopes? So one thing I basically forgot to say, sorry about that. I need to go back a little bit, because I have been talking about these slopes, but there's one more thing that is also interesting. This is the intercept. In this two-dimensional case, it's very easy. The intercept is basically the intersection of our prediction model with the y-axis, and then this beta 1 is the slope. So you need to find both if you have a simple model. So you need to find this intersection with the y-axis, and you need to find this slope. And you don't want to do that by hand, of course. So there are algorithms defined to do this for you. And those are typically called least square. They solve this so-called least squares problem, basically minimizing the sum of squared residuals. I know this looks a little complicated, but we won't dive really into that. So you can do that in 2 ways. You can do it analytically. So there's basically, mathematicians have come up with an exact solution to linear problems. They always know this is the best, but it requires a lot of very costly computer steps to actually calculate those. So you can see this X is actually our set of data, and then we need to multiply basically our data sets once, and then calculate some inverse of that. If you would think about you have 1 or 2 million data points, that's actually, I'm not sure that whether your computer is going out of memory, but yeah, it's basically not a good idea to do that, because it's maybe your computer can even handle it. So that's why we need approximation tools, and that's in the form of a gradient descent. Again, I won't dive into detail, but typically when you're using linear regression on a large scale, you won't use the exact method, the analytical method, but an iterative algorithm that finds the best set of parameters for you. So the best intersection with the y-axis and the best slopes. So yes, this is the bit on linear regression. So I think I now have time maybe for 1 or 2 questions.
Yeah, let's see.
Question: in the case of we got RSS 0, does that mean we are over? Good question. Yes, you need to check that. So so suppose you would have a residual sum of squares of 0 with just one x, then I can't really say that you're overfitting, because that's basically the simplest model. But again, that yeah, you just need to practice a little bit with that. Again, we will see that tomorrow, how you can do the overfitting. So don't see any other questions. So I think then it's a good time to start doing the exercises. I will of course also be available to answer questions during the exercises. But for now, let me show you how we can do the exercises. Because normally I would highly recommend to have a local installation of Python and then add your libraries to Python, such as you can do everything on your machine. I have, from experience, I've seen that that takes a lot of time to set it up. That's why we're going to use something called Google Colab. So I hope everyone has a Google account. And with Google Colab, you're basically going to train models on the cloud. So this is already about the bit. We don't need very good computers because we can do it on the cloud. That's basically what Google Colab is doing. It has already Python installed for you. I think it already contains the most used libraries. At least the libraries we're going to use are available in that Python. And I see, can we take a short break after the exercises? Yeah, definitely. But I would recommend also take a break if you already need it during the exercises, that we can just, I will say we take, I think, half an hour, and then you are just your own responsibility to take a break whenever you need and work on the exercises, if that's okay. That works typically best with larger groups. So if you're in Colab, what you first need to do is upload a notebook. So you can see here under File, there's an option called Notebook. You can browse your computer. I will show you where you can download the exercises for today. I already have the exercises on my local machine. So a notebook typically has this IPyYNB extension. So in this case, we're going to do the linear regression. So you say, okay, I want to upload this notebook. And yeah, that's it. The only thing you then need to do is upload the data. So you can see we're using this USA housing data. What you then need to do is click on this site button here called Files, and then you can upload the corresponding data set, which is in this case USA housing. What this is doing is just making sure that during the runtime here, your data is available, and then everything should be working fine. I'm not sure whether you have already worked with Colab, maybe in a different course. But yeah, it should be simple enough. And otherwise, I hope this small demo was good enough. And otherwise, I hope you can also help each other, making sure that everything is working. So in the first exercise, it will be simple. So you can see I typically already filled in a lot of things for you because it's the first exercise we're doing. So it shouldn't be too hard. And the main exercise here is to fill in the ellipses here. And there are some bonus exercises if you're very fast. And in the first exercise, you will have a data set containing houses and with a certain price. And the idea is to predict, based on the houses, the average income of the average house age, or the average number of rooms of a house, the average income of the area. So might be a little bit fake what I was trying to say. The data set contains the average information of the houses in that area. And then based on that, you want to determine the average area income, giving some insight in which areas are more wealthy and which are not, with linear regression. typically these exercises should be self-explanatory. At the end, when I will try to do is walk you quickly through the exercises together.
David, I mean, we've worked with Colab before, but can you just go back, please, how to upload the
fine
example here?
First, because then maybe already a couple of people can try it. I'm not sure if you already downloaded the exercises for today, but it is in this machine learning directory on the GitHub. Then in the exercises folder, you can see there's a k-means, a linear, a logistic, and a water potability notebook. We will use all of these, not today, but during the course. And then there's this data folder containing the data. But then I will do once again an example. So I will just upload a different notebook. So if you go to Colab, there's this file section. Then there is upload notebook. So then you can say browse. If I'm going too fast again, please say it. So I will now upload a different one. So for example, I will upload logistic regression. So it requires you to download the notebook yourself on your local machine and then upload it to Colab. So this is a different one. Again, it's important to upload the data. So in this case, if I want to run this notebook, I need a different data set. Again, on the side ribbon, there's this directory folder where you can upload runtime data. And then again, you press this file. Is there no way? Sorry, yeah, I have not that much of experience with Colab and because I'm not allowed to use Google accounts in my own work. So I don't know if you can set up, would be nice indeed. But for now, at least uploading would work. Is probably the easiest approach here. So if you want to upload the data, you just pick your data, which is I think hard CSV in this case, and then you will see hard CSV is available.
I mean, I'm sorry, but I didn't see that in the GitHub that we were supposed to download this. I'm trying to open this, but currently all I get is on GitHub, there is an error loading the folder contents. So I'm not sure if anyone, that's just me or where to find this data to download it from GitHub.
Is everyone having that same issue?
I succeeded to download individual files. Like I tried cloning the repo earlier, but that failed. So now I just download individual files and that works for me.
All right. So I think individual files downloading basically means you have to press the file and then press download, right?
Yeah.
Yeah, I think that's, although it's not efficient, you just need to download now 2 files. So you need to download the USA housing.csv in this way with just pressing the file and downloading, and you need in the exercises folder, you need to download linear regression handout.jupyter notebook. Again with this
Can
button.
anyone maybe just post the link to the chat?
Yes.
Because I still get the error.
Yes. I should be, hopefully that this works.
Cool, thanks. No, I don't know. I get a 404 error. I don't know what's going on.
If I can suggest something, if you attended the first class on Python, we have already done that with Google Colab, and you can just copy paste the code that was presented by the other professor and just change the data name. So you can upload your data in the same folder, and through Google Drive, you just do that. It's easier. Just copy paste the initial code that we had, I think it was 2 weeks ago. So I've done that, yeah. It worked.
That would work in practice, but my problem is that I can't get to the file on GitHub. I can't even get it onto Google File.
Is there some authentication issue then? Can you just go to the normal GitHub of Analytics for a Better World?
Yeah, that's where I am. That's where I keep getting the error as well.
Yeah, so it doesn't seem to be related to specifically my content, right? I think it's more
Martin, you just put the documents in the chat.
Yeah,
so
okay, if that's
here
possible.
in Zoom, so maybe you can try that.
Yeah, sure.
To download it from there. It also seems to be working for me, and I can also download it. But
linear regression. Yeah, so let me just do, I think No, okay, that didn't work. How to upload? Is it this one? Okay, yeah, I think that should work. I will try to upload it here. So linear regression handout. Let's not upload. Oh, okay, someone was already. Thank you, Martina. Someone was a little bit faster than me. So again, hope then in this case just download the files from the chat and then upload them again like I showed before.
Yeah, thanks, that worked.
Yeah, awesome.
David,
I don't actually know. Sorry?
There seem to be multiple
upload.
people having an error in the third code box. I don't know if that's something you could resolve. I posted a screenshot in the chat.
Could be that you uploaded it in the wrong folder. Let me see. It's very hard to. So
yeah,
sorry.
I think the error message has to do with that you have to, to do the exercise, you have to fill in the text in the ellipses. So
right.
It's not complete yet.
Exactly. If you try to execute a file like this, where you have these dots, it will complain because you first need to fill in the ellipses.
Okay, thanks.
Yeah. Question to Marta. I'm not sure what is the best practice here. Is it easiest to just keep everyone in this room and then that I can answer questions of everyone, or is it probably better to move everyone to a breakout room, or not everyone to a single breakout room, but move to a couple of breakout rooms?
We could move, but then everybody would need to just post their questions in the chat or call you to their breakout rooms, and you can answer to their question. How long will this exercise be?
So I want to take time until 2:05, so 25 minutes.
Okay, then maybe it's better, to move everybody so that also if people want to take a break, they can. Okay.
Let's try. I see we have 70 people.
Let's see.
So
Let's see. I think we can create it directly.
Any recommendation on the number of breakout rooms, like 4 or 7, something between 4 and 7 or so?
We can do. If we do 7, then it's 10 people each.
Yeah.
Okay. Then I can create it.
Yeah, so before we go to the actual breakout rooms, let's take until 2:05, and that includes a break. And then we have still 2 hours left for 2 smaller bits of theory, so we don't need to be very rushed or feel rushed, let's say.
Okay. Okay, so should we open the breakout room now, or?
Yep, please. Yep.
Okay. I opened them, so you should start joining.
Again, I will also show you. I always scare because of this meeting gets recorded. Yeah, I think I'm sharing. So I will also show you one more time how to upload the data, because I saw some people were still struggling with that bit, and it's a little bit tricky and finicky to get it working the first time. But at least it's the most robust way to do it on such a large scale course. So first of all, I already did this, but you should do upload notebook, and you should have downloaded both the notebook and the CSV. So upload notebook, make sure that you will see this screen basically. And then what you can do is just upload all data in one go, but you can also look at this cell, which is typically at the start of a project. Is it's saying I need to read the USA housing CSV. So what I do, I go to the sidebar. Manage sessions, please give me a runtime. Disconnect. Terminate all the sessions. Connect, please. So if you have this problem, you should reconnect to your kernel. So I'm not sure if everyone faced this issue, but this is also a possibility. Then you see, okay, I need to upload this housing CSV data. Then you go here, then you go to this folder. You should not touch that, but just this upload to session storage. And then pick the USA housing CSV. Yeah, it gives some warning, but it basically means that when you refresh your session, the data is gone. So the data should be in this folder. If you uploaded it in sample data, you should change this cell to, I'm going to read from sample data, USA housing. But for now, the data is in the same folder as the notebook. So what I can do now is start executing. For people that are not familiar with these notebooks, you have notebooks consist of cells of Python code, and cells of Python code can be executed separately. So you can see I now just executed only this bit of code, and it gave me this check mark. So everything is fine. Now I can move on to the next one. I, by the way, execute these cells with Shift Enter rather than hitting this plus sign. Both work fine. So now I hit the Shift Enter, and you can see I added this command df original.head, which is showing you the first 5 lines of data. So you can at least get some feeling of what kind of data you're seeing. So you can see at least the average number of nums is somewhere between 7 and 5 or so. Then I call this typically df original because this is my raw data. I might be doing some transformations to actually be able to execute the model training. That's why I always keep one set of original data so you can always go back to that. Then when I want to do manipulations, I typically make a copy, and then a copy is stored in a new variable called df. Then next step in a typical project is to pick your features and your target. So features is your X of your data with all the features. So in this case, I already gave you the list of features, but the list of features is basically exactly those columns I need. So this price you can see is this column. And I did it also for all of the others. And then you need to pick your target. So the target was to predict the price of a house. Oh no, sorry. This should have been, not sure if that's also in your notebooks, but it should be predicts the average area income. So sorry, at some point for the previous course I gave, it was predicting house prices, but for now it was better to do area income prediction. So sorry, that should have, yeah, it's a little bit misleading. Sorry about that. The idea is here to put in the average area income as a target because we want to get some insight in which areas are poor. So when I execute this cell again, you see the check mark, so we're fine. Although so for the next cell again, we did not really cover why you should do this and how, but this bit is basically saying I want to have a specific train set and a specific test set out of the original data I have. So those two were the ellipses. So I say my feature data and my target data should be split, and I want 30% of my data to be test, which means 70% of my data should be train. And we can actually validate that. So you can see if I add a new cell, new code, so you can see if you look at xtrain.shape, so shape is giving you the number of rows and columns in your train data set. So you see 3,505 columns, while actually the normal shape was 5,000. So you can see we only have now 70% left of our data. This random state thing here is basically saying normally this algorithm or this function gives you every time you executed a different set or a different data set because it does a random split. With this random state, you basically set the random seed such that every time you execute this cell, you get the same result. I see a question, or is it from Eva or?
Yeah. Just a question. The test size here, it's 30%. Was there a reason for this choice? Is there
No,
any?
this is random. So this was just to help you get two different data sets. We will discuss later how you can actually just choose this. It was just to make it easy. Yeah, good question. And then this is actually the only line of code where you train your model. So it's actually pretty straightforward. So we have this linear regression class from scikit-learn, and there's a fit method on the class, which is saying fit linear model. The first argument should be x, and x is training data of features, and y should be your array shape like target value. There is exactly those x train and y train regenerated in this cell. When I execute this, I have now a fitted model. Then if I want to understand how my model works, because we talked about slopes and intercept, I can check my model. Basically, coef is giving you all the slopes for the separate features. So feature 1 has this slope, feature 2 has that slope, and so on. And intercept is again the value of the intersection with the y-axis. So you can actually see, okay, I trained my model, but it also gives me exactly the slopes for each different feature. So that's very nice. I actually did not execute the cells, I think, but it was there.
Can we plot these coefficients and interception?
Plotting. So we could do that, but yeah, you can make basically you can just use this to make a line. But I will show you later on how you can do that. Okay. There's also a cell about that, but you can make a picture out of it. Yeah.
I have a question about the coefficients in
yes.
between. So can you say something about like, is there a relation between how big the coefficient is and how much variance it explains in your model?
From these coefficients, not. And you have to be very careful here because you can see, oh, this is a very big feature, so it has a lot of impact on my prediction, right? Because if that one changes 10%, then you basically get a 60% deviation in your target. But you also need to take into account the magnitude of your feature, because if your feature only ranges from 4 to 7, that is a very different range than looking at the average area income. So this is feature 1. So this range is around 80,000, and then you have a smaller coefficient. So if you want to actually look at feature importance, I think you should look at something like standardized coefficients. I think it's called like that. Then again, that's the bit where you should normalize data and make sure every data is in the same range. Then you can get some feeling on which features are important. But from these raw features, you're not able to do so. Okay. Next, so basically you can make a prediction for your training data set. So this will give you really like predictions for all your observations in the train data set. So if you look at prediction train, you can see it's an array of the average area income that we predict for each training observation. Same here, we can do it for the test set. And then we can actually start doing some calculating the R-squared. So I put a little bit more stuff in here that we have not covered yet, but we will cover later on. Basically just showing there are more performance indicators than just R2. So you can see in this small method that I built, I basically call this R2 score with the actual predictions compared to the, So the actual value, so the actual labels, the actual average area income and the predicted average area income, and calculate the errors and then calculate the R2 score. So you can see in my training set, I get 0.84, which is pretty good because it's close to 1. And in my test set, I get something very similar. So this is already a little bit of a hint how you can check overfitting. If your test and training scores are very similar, you're basically okay. But if there's a large gap between them, then you probably need to check your model again. So for example, if your training score was 1.0, but your test score was 0.5, that's a pretty big gap. Maybe revisit your model. Finally, you can also plot your predictions and then also compare them to the actual just to see that you're actually doing some kind of a linear prediction. And this is actually exactly what is happening. If your actual is going up, your prediction is going up. So you're basically making a good prediction. A perfect prediction would have shown you an exactly 45-degree line. But yeah, of course, we made some errors because we didn't have an R squared of 1.0. This is basically
the cell for the plotting is giving me an error. Per column arrays must be each one-dimensional.
Yeah, I don't know what happens then. But yeah, I think it's probably best not to cover that. I will just give you exactly this notebook. At the end of the course, I will upload this notebook with all the exercises, with all the filled-in stuff, so you can rerun it yourself and experiment a little bit, if that's okay. Just for
actually,
sake of...
up until the cell before it, all the values I received are similar to yours.
Okay, that's good. Yeah, I don't know what
Just,
happened there, but maybe we can spend time in the next exercise together to have a quick check or something. But just for the sake of time, I think we should probably continue with the next bit of theory.
Great.
Sorry about that.
No worries, thank you.
I hope this is fine. Again, I will upload this answer notebook also to the same GitHub, and you can download it and play around with it yourself and make sure you understand everything that should have been there. Again, I just want to show you that this notebook, if you want to, for example, train a random forest or something else, what you would do is just type this, and for 90% of the time, this is just the only thing you would do for training a random forest. Of course, random forest is not a good example because random forest is for classification, so we should use random forest regressor. But typically, the structure of a notebook where you train in random forest or linear regression is very similar. I just wanted to show you that if you know how to do this, then it's not that easy, difficult to go to something more complex.
Can I ask?
Yep.
Okay. When we select the feature vectors, so is it like, for example, in here, is it something we have a know-how in order to help us predict? Is it important to have a know-how the features that where we bring it, or it's not that important for our prediction or model?
So yeah, of course, the feature selection is typically something that's important for a machine learning project, but for now it's just an exercise, so we don't spend a lot of time on that.
Also, I have a question, like how do we investigate the cardinality of high overfitting? At which percentage can we?
Yeah, again, we will cover that tomorrow, so we will definitely do that tomorrow. But for sake of time, sorry, I need to cut off the questions and move to the next bit of theory. We will move to logistic regression. And what we will do in this, because logistic regression, although it says regression, you use it for classification. I really don't understand why. That's just the way it is. We will derive let's say, the algorithm for logistic regression using linear regression. So I think that's something really nice in this slide deck. So again, we will use it for classification. So typically you use this for labels like M or F or true or false. Another nice example is this one, where you where you have a written digit and you want to identify which digit it actually is by a computer. So what you could do is, so you see you have an image So you can basically use the pixel intensity, because black and white have different pixel intensities, to see where was drawn, and that will be, let's say, input to your model, and then the actual output, or labels in this case, will be the actual label that the computer needs to predict. So that will really be 0 up to 9. So we will use a very easy example to derive logistic regression naturally, let's say. So in this data set, we have 14 observations, so 14 persons, and we only measure the height of the person. Based on the height, so we basically have one predictor and one response variable, we want to predict the gender. So the easiest thing to do here right now is just say, let's plot all these observations on a line, because we just have one dimension. So this is a one-dimensional representation of our data. Nice thing is here we can actually plot our labels to get already some feeling. Can we see some kind of relationship between height and gender? So what we see is that there are more M labels at the right and more female F labels on the left. And then in the middle here, we have some, yeah, a clutter. So the next question is, if there would be I hope that's, yeah, exactly. If there's a new unknown person with a height of 172, we want to make a prediction on the label. But the question is, how do we actually do that? So the simplest thing here we can do is say we draw a so-called decision boundary, where every new person to the left will be one label, and every new person to the right will be the other label. So for example, if we would draw the line at 185 or something, and we say everything to the left is F and everything to the right is M, so we have at least 3 things right, but you can see we make a lot of mistakes. But for the new person, then it has 172, which is then smaller than 185, which means it will get label F, which is exactly like this. So this is actually a better picture to tell this. So you can see we draw the line, and everything left will be female, everything right will be male. So in this case, because we picked the decision boundary like this, it will get label F. The question is, of course, we now set this decision boundary like random. There are methods to do it, and we will discuss that also later. Okay, this is one approach you can look at it, but why actually develop new tools if we could just do it with linear regression? Couldn't we just linear regression? So the issue, of course, with that is that F and M are not really numbers, so you can't train on that. But that actually doesn't really stop us, because what we could do is just define that the label M should be a 1, the label F should be a 0. Then we have numerical data, although it's not actually continuous, but still we have numerical data, and we could actually try to fit a line through the data now. So you can see we can just plot where M is 1 and F is 0, and that basically means we can now draw a line. So this line would be fitted on this data set. But now we actually want to see if we can start to interpret what this line is doing. So for classification, you could actually think of this line as the probability, because the probability, because this is between 0 and 1. We didn't choose 0 and 1 randomly, because 0 and 1 gives us maybe a nice interpretation of the prediction, because the prediction then we hope is also somewhere between 0 and 1, which you could see as maybe a prediction probability, meaning that it will give you the prediction that it will be label M. But then we get a little bit of a weird situation here. So of course this is then prediction probability 50%. This is exactly the decision boundary that might be optimal, because everything, if we think we are more than 50% sure it's an M, let's give it an M. But if we are less than 50% sure, let's give it an F. But if we look at the the problem in this way, then you can actually start to wonder, what does do these weird tails mean? Because then this tends to, you tend to interpret this then as the prediction probability of less than 0%, and this is a prediction probability of larger than 100%, which is kind of weird. So the question here is, can we improve such that we do something that's pretty similar than linear regression? Because line fitting, we already know how to do that, but that it also has the properties that it will never predict more than 100% or less than 0%. So what we could start to do here is divide our data into bins, and a bin has basically how do you say that? You say the bin has a left and a right boundary, and everything that is between the left and the right boundary is put into that bin. So if you have a bin here between 169 and 170, I put in every data point that's between 169 and 170, and then I count the number of labels I have. So I count the number of Fs and M, and then I determine the fraction of that label in each bin. This might go a little bit fast, but we just want to know the percentage of labels in each of these bins. The nice thing here is that because the way we calculate those percentages, we always know it can never go below 0%. Because if we have 0 F labels but 8 M labels, then we have 0% of that and 100% of the other. So we'll always be somewhere between 0 and 100. And the nice thing here is that we actually start to see some kind of a S shape here, which is nice. And then again, we can also just use this kind of an histogram approach to do a prediction, because here again we get we can say if we have more than 50% of one label, then we are sure that we should use that label. So you can draw this 50% line again. Then if we have in this case, for example, a new observation of 172, we go to that specific bin, which is I think, let's say 172.1. We will be in this bin. This bin has around 80% F and 20% M. So 80% is larger than 50. So we will classify the new one as an F. So that's let's say a different approach, and that's probably a better approach than what we used for linear regression, because we now have those nice features. Problem with this one is that we still don't have a formula for it. So that's the bit where logistic regression comes in. They have found a shape that is exactly doing this, and it's called the sigmoid shape. And this sigmoid shape has exactly the properties that we want, because it will never predict below 0% prediction probabilities or above 100% prediction probabilities. Again, with logistic regression, we exactly transform one of the labels to 0 and the other label to 1 to actually fit the internally the model. So I won't dive. Yeah, okay. So this is the actual model. So I will not again derive why this is exactly having those properties, but you could try to derive why it has those nice properties of asymptotically growing to 1 or asymptotically decreasing to 0. So if we make a prediction now with the sigmoid function, we use this very complicated looking function where we have a natural, what's it actually called? And the natural exponent. Actually, don't know. Sorry about that. So E of something called a linear model. So in this case, you see you have one intercept again and one slope, or that like we had in linear regression, but instead of just having this linear model, we do it to the power, so e to the power of that model. And this is now how you actually do logistic regression. If you now want to, for example, do the height, you just fill in 172 for the height, then you get your prediction probability. Based on the prediction probability, you can assign a label. And I think at some point we already covered this a little bit. So typically you just say, okay, if you are more than 50% certain, then you assign a label. But in certain cases, it might be beneficial to choose your own decision boundary. So maybe you say, I need to be very, very sure. Then you can also use a decision boundary of 0.9 or of 90%, because you just want to make sure that you don't falsely predict, because it could have devastating impact. Think, for example, when you would assign some kind of medicine to a person, then you want to be very, very sure that that person doesn't have any side effects. So then in that sense, you don't want to use maybe 50% certain, but you want to be 80% certain that this person is not going to have any side effects. So these are just use cases and context that is very important when choosing your decision boundary. Yeah, so you could actually look at logistic regression as a small modification of linear regression, except that you use it for classification problems, and we need a decision boundary in the end to transform those prediction probabilities into an actual classification of the label. But that's it about logistic regression. Sorry about my throat.
Yeah, we have some questions.
Yeah, I'm also just checking the time. We only have 1.5 hours left for 2 more exercises and some additional content. So maybe we can do 2 or so. Let me just.
Yeah, it's only 2 questions.
Oh, it's only 2 questions. Okay.
Yeah. So the first one is, this prediction is using only one variable, which is height, which means the error in prediction is higher than using 2 or more variables for prediction. Is it right?
Yes. So if you use more predictions, you probably have the same accuracy or better of your model. But again, you could start doing overfitting.
Okay. Are we going to see how to predict based on multiple variables?
So I'm not going to explain it. But if you need more, then you just add more. So the funny thing is with the logist in Python, it doesn't really matter how much features you have. So this logistic regression works for both one feature and multiple features. So that works fine.
Okay. And then there was a bit of a discussion is E Euler's constant, which is 2.74 or 2.71.
I think Euler's constant seemed to be, yeah, I think that's, no, it's not Euler's constant because that's something else. It's Euler's number. So, but yes, it is equal to that point, 2.718. Yeah, but that's actually called Euler's number. Just looked it up because I also forgot about it. But yes, it's 2.7. Yeah.
Okay. And we can do this and then open the breakouts. How do you adapt logistic regression from a binary Y to a Y that has more discrete classes?
Yeah, so typically you do multiple logistic regression. So I think logistic regression only works for 2 classes. And so what you then do is you say, I want to predict. So if you have A, B, and C, then you say, I do 3 problems, 3 regression problems. And I say, one is I want to predict A and not A. So not A means B and C. And then next step would be, okay, I also want to set up a classification problem for predicting B and not B. And we want to have a prediction problem for predicting C and not C. So you need to split it into multiple sub problems in that case. Hope that's clear. But we don't cover that in the exercises. In the exercises, just an easy yes or no.
Okay.
Thank you.
So in the next exercises, we are going to cover it's called the logistic regression handout. So again, upload that to your notebook. And you need to have the heart.csv data because we have basically data about a heart and we want to predict whether someone has a risk of getting a seizure, I think. So again, make sure you download the notebook and the data, upload both, and then you should be good to go. Again, I want to take half an hour for these exercises. So let's go back at 5:10 past 5. I need to take a short break because my throat is a little bit sore, but I will be back in 10 minutes to cover some questions.
Okay. So let's open the breakout rooms and maybe save your questions for when David is back.
Yep. Let's wait until I see again the 70 participants before we start again discussing the answers to the exercises.
Sorry, I was changing the decision boundaries in the last section, but the same number was coming up, so nothing has changed.
Yeah, okay, I will spend a little bit more time on that bit then. I will show you, because maybe the difficulty with changing the boundary is that you need to actually see if the model, if it actually makes sense. So in certain cases, changing the decision boundary could result in no changes. That could work. That is possible. But I will spend a little bit more time when we reach that. Can we see if everyone is back, Marta?
Yeah, I think everyone is back.
Okay,
everyone
awesome.
from the breakouts.
Thank you. Then let's go over the exercises. So in this exercises, I just also wanted to show you that although scikit-learn is probably one of the most used libraries for machine learning, it's not necessarily the only one. One other famous one is stats models. And in this case, what is a little bit confusing is that the interface works slightly different. I've seen already quite some questions about it, so let's spend a little bit of time on it. So again, we need to read the data, and here already you can see a start of where it becomes a little bit vague, because we need to manually add an intercept column. Because if we don't do this, the model will by default not fit an intercept, meaning that it will only fit one of those slopes for my features and will basically skip the whole intercept. So what we do, we basically force the model to consider an intercept. And that's why we manually add a column of only ones, which is basically just a constant, meaning 1 times the fitted coefficient of logistic regression will end up in that beta 0, or the intercept of our logistic regression. That's also why if we want to consider the features here, we are not only considering the cholesterol of this data frame, but we also need to consider the intercept as a feature. Otherwise, it will still not fit. So in this case, we end up with 2 features and 1 target, and target is just target in this case. So that's easy. And then you have seen that this interface again works slightly different. And this one was talking about endogenous or dependent variable and exogenous, meaning independent variables. Again, independent variables means features. Endogenous or dependent variables means target. So that was why it's so important to know it's not only features and target, but there could be different names. Otherwise, it's very hard to fill this properly in, because in this case, it is not x, y, but y, x. So this also requires slightly different initialization of your model, because you need to supply the data upon creating the class. Then you can fit. So this is where you are going to fit your slope, your beta 1 and your beta 0, the intercept. And then there's this function summary to give you some insight in how it derived all the coefficients. This is a lot of statistical output, so only look at it if you know what it is or are interested in that. But at least give some insight in whether each of these features is actually significant, if in, let's say, statistical terms. But you could skip that for now. Then again, we can look at the features. So these are now the, sorry, I think I just did not run this one. So you can see this will be the slope for the feature, and this is actually the intercept. So the intercept is actually itself also very close to 1. And this might also be a little bit confusing. So now if we want to make a prediction for someone with a cholesterol of 50, so you need to fill in 50 and 1, because again, we need to make sure intercept is filled in correctly, and we consider the data for the intercept always to be 1. So this is always like cholesterol value, 1. So if you want to do a different cholesterol value, maybe 150, you should do something like this. Then this exercise was just about filling in this manually. So normally I would also talk about odds. That's also why I said just skip this part, just fill in the whole formula. But I basically made it myself a little bit easier, that I don't have to write the exponent multiple times. So you can see this whole exponent plus the 2 parameters. Now let's do now 150 in our case. And then you do the exponent divided by 1 plus the exponent thing. And then you can check that the manual thing you calculated is exactly the same thing as the thing you see. So now it also becomes a little bit more clear that if you would not have added this params here, you wouldn't have this thing. So if you would forget about it, you basically have 0 intercept, and you will end up with a completely different prediction. So that's why you really need, if you want to intercept, you need to add it yourself. Then of course the idea here is that typically with Python you don't want to do predictions for each observation separately. So there are some lines of code how to do it in one go. So first we do a predict, and then do the, okay, so this is very easy. If you use the model, you just do predict, and otherwise you just need to multiply it with x, the column of cholesterol. So again, these two things will give the same thing. And then we can actually investigate a little bit what the predictions are currently. So prediction props variable contains our prediction probabilities. So you see, it's actually not a classification yet. It's really prediction probabilities. So what we want to do now is convert it to a classification, and that's where we use the numpy where function. So we check everywhere where the prediction probability is larger than 50%, we assign a 1, and otherwise we assign a 0. So if I add a new cell here below, you can now investigate that this thing contains ones and zeros is the actual thing we want. Suppose you want to change something else because you want to be more sure. You can, for example, change the decision boundary to 80%. And now you will see that this thing is 50% certain, so should become a 0. So you can see when changing the decision boundary, your labels in the end will change. And based on the decision boundary, you can also start to compare how many positive predictions you made. So you can actually see with the current decision boundary of 80%, we only predict zeros. So in this case, that would not make a lot of sense. You probably want to actually use something like 50%, and then you can see we still have way less. Oh, no, okay, we have now way more, sorry, positive predictions, but still, we actually have way too many. We made quite some mistakes. But again, tomorrow we will see how we should deal with these kind of situations. I see someone is saying, I am lost. Maybe that one is good to just cover. Otherwise, but which bit was unclear? Maybe I see a hand raised by Eva.
Yeah, I don't have a question. It's just I see more people in the chat have the same problem as me. When in our codes we present the results saying actual number of heart disease diagnosis, and then it formats the 165, 0, 138 in a different way, and it's difficult to interpret. Like it looks like we get 4 results back, and we don't get a matrix. It's more difficult to interpret what's the 1 and the 0.
Exactly. So typically you would actually present this in a confusion matrix, but we have not covered that bit of theory yet. So yes, I agree. These lines might be slightly difficult to read, but you have to see this is the bit about the actuals. So this is the actual. So in this case, we have 165 actual heart diseases and 138 no heart disease. And then we look at what did we predict. We actually predicted on the whole data set that we had 260 heart disease. So basically we predicted 95 too many. That's how you should interpret these numbers. Again, if you're lost at this bit, don't worry, because we will cover this way more in depth tomorrow, and then it will become way more clear how to handle this. This is just to show you a little bit how you can also do it in Python. Hope that doesn't scare anyone off, but tomorrow we will cover it in more detail. Because I see we only have 40 minutes left for today. So I would prefer to move to the next bit of theory, if that's okay. Yeah. Someone says, okay, just a list of 4 values. Yeah, then it becomes very difficult to see what you're actually talking about. Yeah, tomorrow we will show you how to properly represent these results such that you are not confused anymore. Again, I will make sure after this session that this notebook is also available, that you can just walk through the answers yourself and hopefully get a little bit more grip on what we were doing here. Let's open the last slide deck for today.
Yes, sir, you can share the notebook.
Yeah, notebook will be shared. I will. I just don't have the time right now, so I will do it after we complete this course. Not the whole course, but after we complete today. So yes, I will definitely share the answer notebooks. Don't worry about that. So last bit of theory will be k-means. Also good for you to maybe for your own expectations. Today is really like the theory heavy part. So this is really almost like 70% theory, 30% exercises. Tomorrow it will be more 50-50. So just to get your expectations a little bit clear here. So we will close off today with one new algorithm, a clustering algorithm called k-means. So again, for what kind of problems do we use it? We use it for problems where we don't have the labels or the target variable. So we only have features, and we want the algorithm to come up with the actual labels. So in this case, we want to have, let's say, a label for cluster 0 and a label for cluster 1. So we need the algorithm to find the labels for each of our observations. Typically for these algorithms, you need to specify how many clusters you need. Otherwise, the algorithm cannot find itself. I think at least k-means can't figure it out on its own. But I don't have a lot of experience with it. So typically you need to say beforehand how many clusters you want, and then decide yourself which clustering is the best. So what does k-means clustering and what does it do? So the idea is that you have n observations and you want to partition it or cluster it into k clusters. That's also what this k means here. So what we basically do is we randomly start with some kind of starting clusters, and we say each cluster has a mean, so the average, and then we need to determine the observation from each, the distance from each observation to the cluster average, the cluster center, and then we basically say the cluster that is closest, I will assign the observation to that cluster. And if we sum up all the distances to the assigned clusters for each observation, we get a objective, because we want to basically minimize the distance for all observations to the cluster. So you can see if we want to do it mathematically, again, that's not very important, but just want to show you what that looks like. It's basically saying those those mu's here are the cluster centers, and then we oh, okay, I see a lot of people need to drop at 7:30, so sorry about that. We continue to 6 o'clock, but I think it is recorded, so please watch the recording and look at the answers yourself. So here we basically determine the distance between the observation and its cluster, square it and sum it for all observations, and that gives us this value within cluster sum of squares. Again, don't worry about the formula, but just know that this is something that you can typically see as an output for k-means clustering. So the algorithm, I want to show you an example and do it step by step. So suppose the most simple example, we have 8 points on a line and we want to apply k-mean clustering here. So in this case, we decide we want to do 3 clusters. Again, we don't know where these clusters are. So what we need to do is set the initial so-called centroids of these clusters. So centroids basically means the average of that cluster. And what we're going to do next is, of course, assign each data point to one of the clusters. So one of the clusters will be orange, one of the clusters will be purple, one of the clusters will be green. So next step, assign observations to clusters. So how do we do that? We calculate the distance for each observation to the centroids. So that's basically distance between this data point and the centroid is this. Then we also need to calculate the distance between the other centroids. So it's basically this and this centroid. Then also we have one more centroid, so it will be this distance. So you can see green is the farthest away, then orange is the closest. So probably we want to pick the shortest distance because that's the thing we want to minimize. So this first data point, because it's closest to orange, will be assigned to the orange cluster. We repeat these steps for all data points. So you can see these 2 data points are closer to this cluster centroid, so we assign it to orange. Then these are close. Yeah, this one is very easy. So you can see this is way closer to purple than orange. This one is way closer to purple than green. So you assign it to purple. Finally, all these are again closest to green. So I see a question: how do we know where those centroids are? You don't. You just pick them randomly at the first step. So you can really pick any 3 centroids you want. The algorithm will find the optimal centroids itself, or locally optimal centroids. So again, you see the green ones should be assigned to the green cluster. Next step here is, because we now have assigned all observations to all clusters, we recalculate the centroids. So we throw away the current centroids, and based on each on the observation of the centroid, we calculate the average. So the average of this cluster is exactly here. So this will be our new centroid. So again, I see a question: why 3 centroids? Because we picked k is 3. So that's it. Then again, we go to the purple cluster. So we recalculate the centroid of the purple cluster, which will be exactly in between those 2 purple. And for the final cluster, we do the same. We average and find this cluster. Then basically, we will continue doing this until the centroids will not move. So I will just play out the algorithm. step by step again. So we will just repeat step 2 and 3 until it converges. And it converges when the centroids don't move anymore. So basically, when you go back to step 2, you get rid of the assignment to each cluster and consider each observation unassigned and start assigning again based on the distance. So these 3 data points are clearly closest to the orange one. Then, so that you will assign that to this. Then it becomes a little bit more complicated because you can see those 2 purple ones, those 2 here around the purple centroid clearly are closest to the purple one. But this one, we really need to double check. But in this case, I've checked it for you and it is slightly closer to the purple centroid than the green centroid. So we assign the purple label. Then the last 2 are clearly closest to the green centroid, so we assign it to the green centroid. Next step, get rid again of the centroids and recalculate them based on the average of each cluster. So again, the orange cluster is basically staying the same. Purple cluster centroid is not the same anymore, so it's moved to the right, and then the green is also significantly repositioned because it's now exactly between those 2 data points. Again, because the centroids moved, we still need to keep on. We are not done yet. So we again throw away all assigned clusters and start reassigning each observation. So again, these 3 are close to this one, these 3 are close to this one, these 2 are close to this one. We recalculate the centroids, but all are at the same point. So happy faces, we're done. Because the centroids did not move with respect to the previous one, the algorithm converges. Typically, the move will not be exactly 0, but you set some kind of threshold that if it moved within 0.001 or something, some kind of threshold you set yourself, then you consider the algorithm to be converged. This is basically how the algorithm works. Of course, this is just one-dimensional, so it's very clear how you can calculate distance on just a one-dimensional line. But it works actually in any kind of dimension, but you use the so-called Euclidean distance. So Euclidean distance in 2 dimensions, you need to use Pythagoras to calculate the distance between the centroids and the centroids and the observation. So this is just a very nice animation. You can see you assign the centroids, which is this one, and that one arbitrarily, and then the algorithm starts refining and refining and refining until the clusters don't move anymore. So the 3 lines you see here are basically the bounds where when you are, for example, left to this bound, you are closer to the orange one, or if you are right to the upper bound, then you are closer to the other one. So basically, these 3 lines indicate the spots where the distance to clusters are the same. I see, is the outcome dependent on the initial choice? Definitely, yes. The initial choice can basically determines the outcome. So that's what why this is a little bit more difficult to actually apply, because it doesn't find optimal placement. So there might be that there's just one optimal, but it can never guarantee that it finds the most optimal one. So in optimization, we typically talk about locally optimal. So in the neighborhood of that specific solution, it looks optimal. So, and then the algorithm returns that solution, but on the general plane, on all solutions you can consider, might not be the very best, but that's just the way these kind of optimizers work. It cannot guarantee the actual one. So that's a little bit of a downside of this. It definitely depends on the centroids you choose initially. Is the center? I just check if there are one more question. Oh, okay. I see that this is already covered, and I see one question: what metric is used to compute the distance? That's basically the within cluster sum of squares I showed you on the first page. So it's basically you just calculate the distance between each observation and its own centroid, and you sum all those distances, and that gives you the metric. Again, because of time, I will move on. because now the question is how should we choose K? And I think that was the funny thing. I think someone already spoiled this for you because someone was talking about an elbow plot earlier, and this is actually what we're going to use to choose this K. So just to give you some feeling on what happens when I choose certain values of K. So if I choose K is 1, I will basically assign all data points to one cluster. So that doesn't make any sense to actually choose. On the other hand, if I choose K to be equal to the number of data points I have, I basically end up that each cluster will have its own data point. So that also doesn't make any sense. So you need to be somewhere in between. And again, this is the bit about underfitting and overfitting. Again, K is 1 is really underfitting because then you have not enough clusters. K is N is basically overfitting because you have too many clusters, and you need to be somewhere in between. And the somewhere in between, you need to determine with the elbow plot. So it's actually not that difficult to do because what you do, you fire the algorithm for K is 1, you fire the algorithm for K is 2, K is 3, 4, 5, a certain amount of Ks. And then you calculate this within cluster sum of squares that we discussed as metric. And then you plot it. And this is actually your elbow method because you make this, this plot looks like an elbow because it has this curve here. And typically you look like you search for the point on this elbow plot that any K after this plot will almost be like a horizontal line. So you see the improvement for this metric because you want to minimize this metric from K is 1 to K is 2 is very big. Also the improvement for 2 to 3 is very big, but then the steps become smaller and smaller. So probably K is 3 might be your optimal choice. Again, might also be dependent on your context and your use case. Maybe you want 3 clusters because it makes sense that you have 3 clusters. So it's also typically something you need to, again, discuss with the persons that are going to use this clustering algorithm that you fitted. And this is basically, there are also, of course, other methods, but the elbow method is the most easy one to implement. There's also something called silhouette analysis, but this is out of scope for today. But I think there are even more methods to check your K. So this is about actually everything I wanted to talk to you about with K-means clustering. So you should use it for clustering problems. It's an iterative algorithm for finding the centroids of the cluster. Be aware that it's dependent on the initial choice of the centroids. And in the end, you can find K by creating an elbow plot to avoid under and overfitting. Okay, we have 25 minutes left for the last bit of exercises. So if you have any questions, I think it's probably best to ask them during the exercises because then 25, okay, we only have 20 minutes because then I have 5 minutes to close off this session. So let's go back to this main session in 5 to 6. And then you should use the K-means clustering exercise, a handout this time in combination with, let me double check. So K-means handout, Jupyter notebook with the country data. And I can share.
Yeah, exactly. If we can share it in the chat, then maybe everybody's.
Yeah.
Thank you.
Yes, I've posted both the CSV and the notebook in the chat. So good luck, and
Okay.
I will again
open
visit
the
the notebook.
rooms.
Yeah. Thanks. Let's give it a minute to see if everyone joined, but I think we probably lost a couple of people along the way because it's probably late in different time zones. So I guess everyone should be back now from the breakout rooms, right? Yeah. Okay, just in the last 4 minutes, let's just walk over the exercises for the k-means clustering. So let's see here a little bit. So here I set a little bit of settings for you that you just should not really care about today. But there are more configurations that you can set for k-means, and it's just okay to use these ones for today's exercise. So not that interesting. This tolerance one is the one that I've been talking about. This tolerance is used to check the move of the centroids, and if it's less than the specified tolerance, it converges. So this is what this one is doing. Here we load the country data, and we are only interested in these features. And so we make our feature data sets, and we don't have a target, so be careful of that. So there are, of course, also methods in pandas to get a little bit more insight in what kind of data you have, just to see the different data ranges. One important bit here in k-means clustering is that it's probably best to make sure that each feature is on the same scale, because otherwise the magnitude might influence the algorithm. And that's why I gave you these lines. These lines make sure each feature is min-max scaled. And maybe I can show you what happens when you do the scaling. Yeah, basically everything should be between 0 and 1, I think. Let me just check that data scaled. Yeah, so you can see basically all data points are now within the 0 and 1 range, which basically means the algorithm will treat them the same way without any interference of the magnitude of the data. Because you can see this one, income is around 125,000, while health is just between 17 and 1. So it's quite different. Then you just want to fit one k-means clustering to start with. So you just use the default settings here. There's a way to import the default settings I set at the top. And then you assign the clusters yourself here. So in this case, we might want to start with 3 clusters, and we get a prediction. And the prediction here is like a number between is a number 0, 1, or 2, meaning this observation, the second observation, is assigned to the 0 cluster, and the first observation is assigned to the 1 cluster. That's how you should interpret this prediction. And what you can do is just add the cluster information now to your data. That might be useful later on when you want to make plots, for example. Then here, this cluster centers is the centers of the clusters that you can see. And then here I have a little bit of code to show the values of the centroids. So you can see the differences between them. So I'm not sure if I can check an easy one. Wait a minute. Because they are now scaled on a 0 to 1, it's a little bit more difficult to interpret the numbers here. But you can see that cluster 2 has the highest life expectancy, for example, while cluster number 1 has the lowest. This is how you can look at your clusters. And this inertia is exactly the within cluster sum of squares we have been talking about. So this is the one you want to show in your elbow plot. And here I have a couple of lines of code to fit the elbow plot for 11 different Ks. So it's pretty fast. So you can see around 4 or maybe 3 clusters would be probably the best choice, because after that, there's not a lot of gain in the within cluster sum of squares. Finally, to get a little bit more insight in our cluster, you could use a pivot table again to get some insight for each data point falling into a cluster. What are the average values? I think this is way more interpretable than the previous one. So you can see cluster 1 has the highest income, for example. So this helps you a little bit, getting a little bit more feeling on what happens with what did the algorithm do. Another one that you can look like, because we're talking about countries, is just look at which countries belong to which label. There's actually a notebook on the internet. I used it here, I think, at the top. You can look at this one. Made actually a geographical plot. I think that's a very nice representation of these labels on a world map. But you can see at least a lot of, I think a lot of African countries are related to cluster 1. Finally, what you can also do is make a 2D scatter plot of your cluster. So in this case, we are interested in child mort versus GDP, and then we can plot that on in a scatter plot and color based on the clusters, and then you can more or less see on a 2D plane how these clusters are lying. So you can see apparently these are I don't know what actually the cluster labels are, but yeah, at least we have a yellow cluster that's clearly formed here, a blue cluster that's formed here clearly, and a purple cluster somewhere here. At least there's some way in a two-dimensional way to look at your clusters. I see we're out of time. Maybe, is it okay to do one more question, or should we just say stop for today?
I don't. Maybe there's one. Yeah, I don't see any specific questions. Maybe only one that came now. The clusters were calculated over all categories.
I don't know what you mean with categories in this case.
Sorry, the columns in the first data frame. So like when we were calculating the clusters, we did that taking into account every single column before.
Every single column, yes.
So in this graph that we were just seeing, it could have been that there wasn't such a good match between clusters.
So you can actually see the plot that I have. Let me share my screen one more time and then we will close. You can actually see that the clusters are not perfect, but that's because we used 7 dimensions and we just, how do you say that? Do some kind of dimensionality reduction to at least get some 2D plot, because we can't make a 7D plot. So probably some other feature separates this one from the purple cluster. So that's how you should interpret this. So yes, they are not perfect here. If you would have only included these features, then you won't see.
Then it would be a perfect match. Yeah.
Exactly.
Right.
Yeah.
Okay. Thank you.
All right. I think we will close for today. I will put in the notebooks answers after when I leave this session. I really enjoyed this session. I enjoyed the interaction between every one of you. I was a little bit not sure how to do it with so many people, but I really enjoyed it, and thanks for all the questions. Hope you also enjoyed it, and hopefully we can have a nice session tomorrow again. So have a nice day. And
thank you. Thank you very much.
Thank you so much.
Thank you everyone for participating.
Cheers.
Thank you.
Thank you so much. See you tomorrow.
Tomorrow. Bye bye.
See you tomorrow.
Bye bye.